Hello everybody. Once more here glad to talk about electrical harmonics with the goal to increase your knowledge about them. If you remember, we ended the last session talking about the triple harmonics, which are zero sequence or homopolar harmonics. They have the particularity that do not cancel themselves. What does this imply? Let's imagine that in a 4-wire network, 50 amps of third harmonic current are running through phase 1 cable, other 50 amps through phase 2 cable, and also 50 amps through phase 3. In this case, 150 amps of third harmonic current would be running through the neutral conductor. Why? Just because triple harmonics per phase are directly added through the neutral wire. What does this may result in? It's clear. The neutral wire could be overloaded, some thermal protections could trip, or even a much more header-show event may happen, the cut of the neutral conductor, which may give rise to a severe voltage imbalance with a great risk of overvoltage between any phase and the neutral that could damage the connected single-phase loads. Another direct effect when harmonic currents are running through the conductor is that certainly a greater RMS current, more amps, are running through them. This additional current may obviously overheat the conductors and make the overload predictions to trip, stopping so the operation of the downstream loads. Troubles can actually also happen in the power transformers, since if they, besides of supplying the fundamental current, that is active and reactive power demanded by the loads, have to also supply harmonic current, their internal losses are also increased, either due to Joule effect, the copper losses, as mainly the iron losses, because these are directly proportional to the frequency. So the presence of harmonic currents running through the transformer windings will make these losses to rise. This may lead to basically two effects. One is a poorer voltage quality, reflected on high voltage distortion rates, affecting the correct operation of supplied loads. And the other is the rise of the transformer temperature that may cause the derating of the power transformer capacity. Let's talk now about another typical effect related with harmonics. This is the trip of residual current devices. It is commonly thought that when harmonic currents run through an RCD, this may trip because of this current, but this is not exactly true. Residual current devices just should trip when detect a leakage current to ground. So, what is then the real effect of harmonics on them? That they may increase the RMS value of the leakage current, especially in the event of high voltage distortion rates. So it becomes essential the right choice of your residual current device. This must be at least type I, that is suitable for alternating and pulsating currents. And in the case of protecting power drives with internal AC to DC conversion, they should be type B, which also detect DC current leakages, guarantees so a safety and a total protection of your installation. We've been relating high voltage distortion rate with a poor voltage quality. Voltage TSD rates over 5% can already be considered as a high grade, and therefore it may lead to a malfunction of mainly sensitive electronic devices. Anyway, it is important to emphasize that although they are commonly blamed for, voltage harmonics do not normally make electronic devices to be burnt. When, for instance, a switch mode power supply is damaged, it is most likely due to an overvoltage event in the power grid. And to end this session, let's talk about what we could call like the top star of the effects of the electrical harmonics, because probably is the most usual and well-known one. The effect on power capacitor installed for power factor correction purposes. First, to better understand this effect, let's look to the impedance curve of a capacitor. As it can be seen, the higher the frequency is, the lower the impedance is. So it can be easily concluded that capacitors are low impedance paths for harmonics. Therefore, if a capacitor is connected to a power system that has some level of harmonic distortion, it is always going to be overloaded in a certain degree. However, this will not usually be the gravest problem that could arise, since this is the parallel resonance phenomenon, which basically involves the amplification of the current harmonics already existing in the network before the capacitor are connected to it. That is, the existing harmonic rates in current and voltage rise when the capacitor bank is put into operation. We must now also consider the parameter known like the order of the resonance frequency of a power system. This value relates the short circuit power at the coupling point of the capacitor with the power of the connected capacitor. In the event that the frequency order of any of the predominant harmonics in the network is close to this value, the risk of this harmonic to be amplified to increase its amount is much higher. This is what is known as a parallel resonance event. But let's use a real example of a resonance event for a better understanding of this phenomenon. In the next session, I hope that you will not miss it, I will explain which solutions can be employed to avoid this event to happen. This screen shows the time plot of the inductive reactive power in this installation. It is easy to observe when the capacitor bank is on or off. Let's look at the voltage and current waveforms when the capacitor bank is off. The total harmonic distortion in current are around 20%, a usual value in many industrial power systems. But in voltage, the total harmonic distortion rates, around 8%, are definitely high. What will happen then if a capacitor bank not equipped with the required component to avoid a resonance event is now connected? It happens what you can see in the screen. No much explanation is needed, indeed. Voltage total harmonic distortion rates are extremely high, over 30%, which for sure will eventually cause some loads to work incorrectly. But the most serious fact is that a harmonic amplification is happening. We can clearly count 5 cycles, that is, a resonance event of the 5th harmonic. This resonance not only means an extreme overload of the capacitors, that this will not probably be able to withstand for a long time, but also that the power transformer is working under untenable conditions. As I told you, in the next and last session, please don't miss it, we will figure out how to avoid this situation, along with solutions for other troubles related with harmonics. Till then, good luck and stay safe.